Complex number 7 minus 4i is denoted by z. Giving your answer in the form a plus bi, where a and b are rational numbers, find the following. So 3z minus 4z star, that's the complex conjugate. Let's just write it up here. You basically reverse the sign on the imaginary part, so it's going to become 7 plus 4i. Right, so here I'm going to get 3 lots of 7 minus 4i minus 4 lots of 7 plus 4i. That will become 21 minus 12i minus 28 minus 16i, which is minus 7 minus 28i. For this next one, you could expand it as it is, but it's going to make much more sense to sub in our z value. So I'm going to get 8 when I do 7 plus 1, and then minus 4 minus 3i, that's minus 7i squared. This is a double bracket, so I'm going to get 64, 8 squared, and then I'm going to get plus 49i squared, so that's going to be minus 49, then minus 56i minus 56i minus 112i, which gives me 15 minus 112i. And finally, we've got some division. Z plus 1 will give me 8 minus 4i. Z minus 1 will give me 6 minus 4i. Now I decided there's a common factor 2. I'm just going to divide through by 2. That'll make it a little bit easier. 4 minus 2i over 3 minus 2i. If you don't see that, don't stress. It will still work out in a similar way because now we times, I mean, you can times by the complex conjugate of this one here. Yeah, but let's do it with the 3 minus 2i. So I'm going to times by 3 plus 2i. That will then get rid of the imaginary part, just like when you're dealing with surds. Okay, I'm going to carry on down here. So I'm going to get 12. Then I get plus 8i minus 6i, so that's plus 2i, minus 4i squared, so actually it's plus 4, all over 9 minus 4i squared, so 9 plus 4. That gives 16 plus 2i over 13. Just got to write it like they've asked, a plus bi. So 16 over 13 plus 2 over 13i. Express z in modulus argument form, given the modulus exactly, and the argument correct to 3 sig figs. Okay, so the more of these I've done, the more I've decided, let's just write down the general equations, which you can learn or you can just derive each time. So if I always draw one in the positive, in the first quadrant, just makes life a lot easier. So I've got x plus yi. Then I can see using Pythagoras that the modulus of z is going to be x squared plus y squared square rooted, and that can be applied for any quadrant. And then tan of the arguments. The argument is this angle here, the anti-clockwise from the real axis, positive real axis, the amount we turn to get along the in the direction of the complex number. So tan of the argument of z is then y over x. So I can use that here. Or then I can say that and by the way, this also then works for any quadrant. In the past, I've like drawn the triangle, worked out the acute angle and figured it out from there, but actually we don't need to. You can just go straight to it. So I've just got into the habit of doing that now. So modulus of z is therefore going to be 7 squared plus minus 4 squared, square rooted, 49 plus 16, which is root 65. Arg z is then going to be inverse tan minus 4 over 7. And it will sort it out for me, okay? Because actually, I'm down here, so I'm expecting to either get something that's, it depends how you're measuring your complex number. I think I'm going to get a negative here, so I'm actually going to be going from 0 backwards. That's absolutely fine. Or you could add 2 pi on if you want to give your answer from 0 to 2 pi in that range. Okay, calculator in radians mode. Inverse tan minus 4 over 7 gives minus 0.5191. Then in modulus argument form, we can say that z is going to be the magnitude, and it's cos of the argument, so cos of minus 0.519 plus I sine minus 0.519. So just a reminder, this comes from the fact that we've got our root 65 here, and we're finding the component of that in the different directions. So if I want it in the x direction, I'll be timesing by cos, because this is the adjacent to the angle. If you wrote down what cos of the argument would be, then you'd get the x part divided by the magnitude. So then you can see that x is just root, so the magnitude times by cos of the argument. That's where that bit came from. And you can do very similar with the y. So just a little explanation there. That is our answer for the modulus argument form of z. Then we've got another complex number omega, such that this is true. We're asked to find the magnitude and the arguments of omega. So omega is going to be the modulus of 585 cos 0.5 plus I sine 0.5 divided by the one that we've just found. Okay, so then it can be shown that the modulus, I mean the causes are just kind of to do with the angle really, whereas the modulus is all about like the length of it. So you can be shown that you just simply divide these two to get the modulus of omega. And if you do that, you get the modulus of 9 and hence 3. Okay, not going to go into further proof on that. That's just something to be aware of. When you times two complex numbers together, you just times their magnitudes to get the magnitude of the new complex number, or the modulus. And with the angles, well, if you're timesing them, then you actually add the arguments together. Here we're dividing them, so we minus them. So arg of omega is going to be 0.5. You can use addition formulae to prove this. I'm not going to do it here. Just going to use that fact. So 0.5 minus 0.519, which gives 1.019, which I'm going to round to 3 significant figures, 1.02. There we have it. Well done.